Okay, so. Unless there are any protests, I'll ask you all again at the end of this, thing. So I'll just, I don't want to do it Wednesday night because it's not for, my usual thing. So Tuesday night would seem to be a good one, so maybe at 6 p.m. I'll see if I can round up a room for that. So yeah, don't forget the resources, right? I wrote you all an email today. There's a couple things, math in, be there. I think that'll be good. And you can study for multiple math classes, maybe even some other ones there. Final exam review, we'll try to set that up for Tuesday. Don't forget about your assessment. You've got one last assessment. And also, if I get a 90% return on the reviews by the time I have to get grades. So you need to do the course evaluations before close of business on the day of your exam. But I don't know if you've looked at the evaluations. Does anybody know when your evaluations actually close? Yeah, I thought I set them to later than that, but I'm not sure. So just make sure that you get it before it closes. If I get a 90% turn, that's another 100 on everybody's list score. So, okay. This is. So the last thing we talked about was this cosets, and I gave this theorem that said what the two cosets are either disjoint or we're exactly alike. So G I looked at these two left cosets. They were either exactly alike or they had nothing in common. And two, any two left cosets have the same number of elements. This is probably most interesting, I guess, in finite, but this is even true for an infinite number of elements, even without cardinality. If this is uncountable, this is uncountable. There's a one-to-one and onto function from xh to yh. This gives this is a very famous theorem, 6 to 10. To run. Let G be a finite group. And A and G a subgroup. Of course, if G is a finite group and H is a subgroup, H is also finite. Then the order of H divides. This is absolutely astounding. So if I walk up to you on the street and I say, I've got a group with 100 elements in it, and it's got a subgroup of order 6, I am lying, because 6 doesn't divide 100. That is impossible. All right. E is finite, and X E as order n, so this statement actually goes further than just the order of any subgroup. The order of an element must divide the order of a group. And actually, your homework reveals why that's true, because one of the things you prove in this homework is the order of an element in a group is the order of the subgroup it generates, right? And so really what this is this means the order of the subgroup generated by X divides. So for example, This is the set of all rearrangements on the Rubik's Cube, right? This actually forms a group under function composition. The order of the Rubik's group is 11 factorial times 8 factorial times 3 to the 8 times 2 to the 4. Do y'all remember me playing with the Rubik's Cube and doing a little twist on it, and a whole bunch of times later it came out? The number of times I had to do that little move was 105, which divides this. 105 is 3 times 5 times 7. So there's a 3 here, there's a 5 here, and a 7 here. So divides that. Lagrange's theorem predicts this. What is the smallest order of an element that you know for sure is not on the Rubik's group? So I did my little twist, and it took me 105 times to take. What's the smallest number that I cannot, by Lagrange's theorem here, I cannot possibly have an element that takes that many times to get back? A little bit. 13. I see why. Every smaller number than 13 divides this. All the powers of 2 are covered, the powers of 3. You've got, let's see, what else do I need? I need 5, I need, well, I've got all the primes, right? 11 all the way down. So you can check that every number 12 or less divides this. 13 is the largest number that does it. And it turns out that for all those numbers, there is an element of that order in the Rubik's group. Notice this says that if X has order N, that divides the order of G. It doesn't say it the other way. It doesn't say that if N divides the order of G, then there's an element of that order. And this actually is not always true. Models order of an element. Okay, so let's prove Lagrange's theorem. It's actually fairly easy to prove. Okay, case 1. What if H is all of G? Then certainly the theorem holds, right? Because certainly if these two are the same, this applies, right? If not, then there exists, I'll call X1 CG minus H. Now look at cosets, right? Notice X1 is not in H, right? By assumption. So notice that, right, X1 is not in H, but it is in X1H, right? Since it's not in H, that means these two cosets must be disjoint. Okay, because that's the bit we proved last time. If X1H union H is equal to G, then permanent. If not, then there exists X2, which is in G, but not in. So let me kind of draw a picture, just sort of for a mental picture. We start with G here. if this is all of H, we were done. If not, it's a proper subset. And we picked X1, it's not in here. So this is going to be the coset of X1 H. If G means 2 or all of G, then we can stop our process. If not, then there's an X2. It's in G, but not these two, right? It's going to be X2H. Here, G is equal to H union X1H union X2H. And done. If not, continue process. Can somebody convince me that this process will eventually terminate? Right? I mean, it's a problem if I can just keep going forever and ever. Explain why at some point this has got to end. Right. G is finite. And every time I'm adding perhaps a new element here, it's not what we've done so far, but there's only finitely many elements in perfect X, right? Everybody agree? So this has to terminate. So what we get is n greater than 1 where these are all disjoint left cosets, right? Since this is a disjoint union, that is to say, there's no overlapping between any pair of these sets, the order of G is the order of H plus the order of X1 of H plus Xn. This takes me back, right? This is the way that we counted the number of elements in a disjoint union, right? No overlap, just count all the stuff in separate pieces and put it together. But what do we know about the relative sizes of all these cosets? What do we know about all these cosets size-wise? They're all the same size, right? That's the other case. And they're all equal to the identity coset, if you will. Order of G is n plus 1 times the order of H. So the order of H divides the order of G. Order of G is something times H, or that's something that's H. Any questions? Yes. What's that now?
How do we know they're all the same size?
How do we know they're all the same size? From the last theorem that we had last time. The two things were, remember, H equals YH, or their intersection is empty and 2. The sizes are all the same. Okay. I am just going to, just sort of for your own culture, in education here, I'm gonna talk about rings and fields a little bit, but just mostly definitions and a couple of examples. We've been dealing with more, they've got one operation, the integers under addition, and that's all we care about. The positive real numbers under multiplication, and that's all we care about. It's also interesting to consider maybe some algebraic structure that has more than one operation. For example, the integers, right? Basically rings are places where you can add and multiply. That's basically it. Now, I didn't say that the multiplication, that the order may matter on multiplication, and some other things, but this is basically the prototype for a ring is the integers. Let me give you a definition here. So this is a ring. And again, sometimes later on, let's stress the operations here. A ring plus dot is 90% such that R plus is an abelian group. Again, think about the integers. The integers under addition is an abelian group because it doesn't matter what order you add to it, right? 5 plus 7, 7 plus 5 doesn't matter. Another operation, often called multiplication, but it doesn't have to be. I want this operation to be nice. How does multiplication behave? Number one, A times B times C is A times B times C. So multiplication, I want it to be associative. There are some people that actually say things that aren't associative, but that's liable to put you in insane asylum, I think. Number two, you want addition and multiplication to play nice together. What do I mean by playing nice together? I mean that A times B plus C is AB plus AC. Anybody know what this property is called? The distributed property. So that's what I mean by plays nice. A times B plus C works this way. But there's something else that I should write. Does anybody catch it? I really haven't written enough. Deal with this. I'll give you a hint. Sometimes this is called left distribution. Also this. If multiplication order doesn't matter, if A times B and B times A are the same thing, I don't, the second one's superfluous, I don't believe either. So for example, in the ordinary integers, I don't really need to write one of them because the order doesn't matter. That sounds like a good thing to have some proof right there. that if A times B equals B times A, then this automatically follows from the other one. See if you can prove that. Let me add to this definition here. I guess it's 3. Additionally, there exists we say that R is with identity. Also, if A times B equals B times A, well, A, B, and R, we say R is commutative. So, examples. This is commutative. Notice that the order of multiplication in the integers doesn't matter. 7 times 5 is 5 times 7, and it's got a 1 that freezes everything. 1 times 8. You might give me an example of a commutative ring that does not have an identity. It's lost its way. You might give an example of. Think of it this way, a set of numbers, probably a subset of the integer, where you can add and multiply, but you don't have 1 in there. Right, but that's a great start. Here's the problem. The whole gets sucked in, right? If you remove 1, well, you've got -1 as an integer, and you've got 2 as an integer, and you add those together, you get the 1 back. So you've got the surgery has to be more serious. Can you even think of an example?
The images be considered a group under like array for the first operation is dealing let's go.
How about the even? Notice this is an abelian group, right? So we've got that covered, right? Think of the subgroup criteria. What happens when you take an even integer and subtract an even integer, you get an even integer? So the subgroup criteria got us covered there. All this stuff is true because it's true in the integers, right? So multiplication is going to be associative and it's going to be distributed, right? But there's no 1, right? Notice if you multiply any 2 even integers together, they get larger in absolute value, right? So, well, unless one of them 0, but that doesn't leave things alone, right? Can anybody give an example of a ring that's not commutative. No, because all those are, you need to be bigger. What's it name? How about that? Two matrices over R or Z. You could have entries in Z, right? When you add two matrices with real or integer entry, you still get it. It's an abelian group. We kind of checked that before. Multiplication of matrices is associative. And guess what? We don't have to do anything awful like you might do in 3110, because we already know that matrices are basically their linear functions and composition of functions is associative. So got that covered. And matrix multiplication is extreme, both sides. This group is not commutative because it's easy to produce examples of matrices that in different orders give you different results. It does, however, have an identity. What's the identity? These last two rings, this last ring also performs a little bit strangely compared to the way you're used to multiplication of the integers. You can, how many of you see examples of this? You can take two non-zero matrices, sometimes and multiply them to zero, even though neither one of them is zero. In fact, there's some matrices that are non-zero you can square zero, right? So that's different behavior. Here's another example. We thought of this as a group. Remember Z mod n clock, you start over again at n. Well, you can do multiplication the same way, right? So for example, one. In Z15, what's 5 bar times 3 bar? Remember what you do, just multiply this by ordinary integers, then you divide by 15 and take the remainder. This also displays this bad behavior that you get with matrices. You can have two non-zero elements and multiply them to get 0. In fact, I'll give you a little challenge here. Well, I don't want to come back to this. Let me give you the next definition. How many of you have heard the word field? Right, where did you hear this word? I heard it when I was mowing grass, but yes, linear algebra would be a natural place to see this too. So is anybody in a linear algebra class where you consider different fields other than the reals? But maybe your professor made it clear that, almost everything that you do in linear algebra, there are a couple of exceptions, but most of what you do in linear algebra, it doesn't matter what field you're in. You can be over rationals, you can be over reals, you can be over complex numbers, things like this. We give you definition 6.3.2. Let L be let L be with we say F is the field if we say that our ring is a field, if when you remove zero, what you get is an abelian group under multiplication. This is true of rationals, reals. Here's another way to put this. Alternatively, what this means under multiplication is if you have any non-zero element in the field, it's reciprocal. This is true of rationals, etc. Here's a little vague theorem. So this one notes, but I was a spider. Here we're going to assume it is bigger than zero. Actually. It's a lot different cases. Right. I'm going to take this given that C mod n is always a commutative of identity. One bar is the identity that's easy to check. This takes me back to properties of the integers. So let a bar be in z on be zero. So think of a as an integer. And what does it mean for a bar to be non-zero? It means whatever this integer is that I put the hat on isn't divisible by p, right? So if it's divisible by p, it would be the zero. Now, what do we know about a and p? What's that? One, right? Because p is prime. So the greatest common divisor of a and p is either one or p. And it can't be p, it can't be p because of this, right? What does this mean about a and p? Do you remember way back when from the beginning of the course? GCD of a and p is one, so what can we do? I remember. So there exists integers.
Quadruple?
Now transfer this. Reduce mod P, that is. A bar, X bar, plus B bar, Y bar, I'm sorry, that would be P bar. One more. All right, just reducing this equation mod P, going back to CP. Well, what's this bit right here? P bar is 0, right? So this is gone. So now you have finite fields for any prime. Right, Z mod 2, Z mod 3, Z mod 5, Z mod 867 309, these are all fields. You can do linear algebra with any of these fields. How about the other direction? I guess we need to prove that if Zn is a field, then N is prime.
Why did this work divide?
Because remember, we're mod P, we're in Z mod P, and P bar is the 0 element.
Oh, okay.
This thing's multiple P, so when I divide it by P and take the remainder, I get 0.
Oh.
Right, okay. This is a great exercise in doing the composite. I think this is easy, you know. So suppose that show that C mod N is not a field. Any ideas on this? Well, this means there exists this is one way we can think about N being not prime. There's two elements, A and B, such that N is A times B. Agree? Now, consider A bar and B bar and C N. These are both non-zero. Neither one of these can be 0 because they're not divisible by N, right? Because of these inequalities here, these are all, both of these are strictly less than N, so not divisible by. Everybody agree with that? So these two are not 0, but their product is 0. Everybody agree with that? Suppose A bar X bar this is a necessary condition to be a field, right? Then X bar times A bar B bar is equal to X bar times A bar times B bar. Everybody agree with that? But this is X bar times 0 bar, which is 0. Do I agree with that? And this is one bar times B bar, which is B bar. And this is a constant. Because neither one of these is zero. So, CN. No. But see now, you all are used to fields that you play around with in linear algebra, like Q and the reals and the complex numbers and so forth. Well, now I've given you infinitely many finite fields that you can play with, which actually this is quite important if you're into things like coding and cryptography and such. Definition. I'm going to give you a definition of something. So I did say earlier that what we can do is we can look at, we can also put other relations on such a thing. So definition, and this is actually kind of, I'm going to need this as a segue into one next. Let F be a field. We say F is ordered. There exists a relation. I'll call it less than on F. Satisfying. So, here's some examples to think of. Rational numbers, real numbers. Number one, X is not strictly less than X. Okay. Number two, X less than Y and Y less than Z implies X is less than Z. So it's transitive. Three, either X less than Y, Y less than X, or X equals Y. And here, of course, X, Y. See? Yeah. So this means it's totally ordered circuit. If I give you any pair of elements, X is the smallest one, X is the biggest one, of the two elements are the same. One and exactly one of those three things has to happen. We have respect of addition. If X is less than Y, then X plus Z is less than Y plus D for all X, Y, Z in F. And it respects positive multiplication. If X is less than Y and 0 is less than Z, then XY, or I'm sorry, XZ is less than X. Oh. Pretty tight. So the real numbers, the rational numbers also satisfy all this. No number is strictly less than itself. If I go from little to big, and then, well, little to medium and medium to big, the little is smaller than big. One of these three things has to happen. If X is smaller than Y, then if I have the same thing to both sides, it preserves the inequality. And if X is less than Y and I multiply by a positive element, then it preserves the inequality. So ordered fields are fields where we can kind of compare elements size-wise. And that's, I think ordered is a good word for it. It allows you to kind of make comparisons on how big things are. Definition. This is kind of my segue into our last chapter. we say the ordered field L is complete. And only if, every non-empty subset has an upper bound so let me give you a couple of examples. And this is kind of a big takeaway from the next section. Let me give you an example. Look at all the rational numbers such that the square of that rational number is strictly less than 2. I can think of a lot of things in this set. 0 is, 1/2 is, right. 1 is an element of the set, 1.1 is, etc. etc. This is equivalent, of course. Actually, it's between these two. X is less than, radically bigger. So, it's familiar with this already. The supremum, there is no rational supremum in this. Right? Because actually, in the real numbers, does everybody agree that square root of 2 is an upper bound of this? And anything smaller than that is not an upper bound, right? That's the problem, right? Radical 2 is not a rational number, right? So if you go a rational number less than radical 2, there's always something in the set that's a little bit bigger, right? And if you go a little bit bigger than radical 2, it could have always done better. It's not a supreme, because, well, R is, and this is going to be actually important in the next section that we go into, the last chapter. So you can take that as an axiom at this point. But let me give you kind of motivation for the next chapter here. Theorem. I'm going to formal introduction next time. How many remember this theorem? Math 1080 for the equivalent. Right. There were two ways that you figured out what the limit of the sequence is. Number one, you reverted to count 1. You treated it like a function, or maybe even did squeeze theorem or something fancy like that. And there was one other probably major theorem in Calc 2 that I guarantee that even the book probably skips over proof, even if your professor skipped over proofs. The book would have probably skipped over this one for at this level. We're done in the appendix. Any bounded monotonic sequence convergence. This was a big theorem, and we're kind of setting up for this. And what we're going to need is our playground. It's the real numbers, and then it's complete. That is, if there's an upper bound of the set, then it's spring there. Okay. Any questions? I don't know if anybody else wandered in, but does April 29th sound okay for me to start trying to? Okay, don't forget, I've got to meet with a colleague, so I don't anticipate being later at about 10:30 hours. I'll get up there as quick as I can. Other than that, I will see you all on Friday.